let's take a look at today's lesson. Through today's lesson, you will be able to explain the classifications of dams according to their construction materials, explain the difference between damage types according to the classification of dams, explain the process of dam safety inspections, conduct key concrete durability tests, explain key geophysical prospecting methods, and match the safety level and state of various facilities. The first section of this presentation will provide an overview of safety inspections. Recently, due to abnormal weather conditions that are occurring globally, the intensity and frequency of natural disasters has increased dramatically and have resulted catastrophic damages and losses of life. Furthermore, the deterioration of dam facilities is also continuously increasing. As a result, the number of the annual cases of accidents has increased significantly, and in some tragic cases, the collapse and damage of many large and small dams all over the world has caused unprecedented financial damage and loss of lives. Thus, K-Water conducts regular safety inspections to prolong the life of dam facilities and prevent public damages in advance. Safety inspections are conducted to discover risk factors innately accompanying physical and functional defects of facilities, and secure the safety of facilities by proposing suitable repair and supplementation methods. Safety inspection of dam facilities in Korea are enforced according to the related laws. The types of inspection regulations are divided into three categories, which are the regular safety inspection, precise safety inspection, and precise safety diagnosis. When safety inspections are conducted, the subject and period for conducting them are provided according to the detailed guidelines. Basically, regular inspections are conducted every 6 months. Precise safety inspections are conducted every 2 years, and precise safety diagnosis are conducted every 5 years. When a precise safety inspection or diagnosis of a facility is completed, a safety grade from A to E is given. If a facility receives a safety grade of A, the period of inspection is delayed by 1 year. On the other hand, a safety grade of D or E means that the period of inspection is moved up by 1 year. A precise safety diagnosis involves more thorough and intensive research and inspection compared to a precise safety inspection, and also includes an earthquake resistance evaluation of the structure and facilities. Before examining the procedure of safety inspections, let's first discuss the various types dam facilities. In general, dam facilities are composed of the body which supports the water pressure by holding water in the reservoir, a spillway which is used to release water during floods, and an intake facility to supply water downstream. Dams can be categorized according to the construction materials, which are embankment and concrete type dams. An embankment dam refers to those using dirt and gravel, while the other type is made of concrete. Now, let's take a look at each of the components of a dam. The dam body can be classified into the upstream slope, downstream slope, and the crest at the top of the dam. The region contacting the existing topography to the left and right sides of the dam is called an abutment. The second facility to be discussed is the spillway. A spillway is an attached structure that can release surplus water during a flooding event in the downstream of a dam. Basically, the spillway provides a way for water from the inlet to flow. The adjustment unit is where the water gates are located, a waterway to release impounded water, and an energy dissipator that protects adjacent facilities from erosion, or scouring on the riverbed by absorbing the massive energy from the discharged water. Other facilities include intake facilities and outlet. First, the intakes facilities are structures in which the water of reservoirs are drawn for human uses such as consumption, agriculture, and industries. The water brought into intake facilities is transported to waterworks, while the water released downstream through outlet generally after use in a water power plant. The process of conducting a safety inspection involves a visual inspection, durability test, and geophysical prospecting. Among these, we will first discuss the methods and order of a visual inspection. Visual inspections help to determine whether there are any defects on the surface of structures, and if so, the severity of the defects. The steps involve directly inspecting the structure on site and recording any defects and damages in a field note, recording them at the office on CAD, evaluating them according to the detailed guidelines, and assigning a score. Ultimately, a state assessment is performed. Let's discuss each of the steps in more detail. To improve the efficiency and accuracy of visual inspections, the facilities to be inspected are segmented into a grid. More specifically, before a site inspection, the following individual facilities must be segmented into a grid form to divide the inspection regions and assign numbers to prepare an external inspection grid network. The inspector performs a site inspection and records any inspected defects and damages on the external inspection grid network to provide accurate locations. A state assessment involves the recording of defects and damages of each member based on the detailed visual inspection results on the diagram, and quantifying the degree of damage according to the detailed guidelines as numerical ranges. On the state assessment chart, the visual inspection network chart, damage types, damage size, damage photographs, and so on are all recorded. Let's take a closer look at how the state of facilities are assessed. The dam facility is considered as corresponding to the integrated structure, Step 5, and the sublevels are divided into the composite member, individual structure, composite member, and individual member. The visual inspection network chart in which defects and damage were assessed by the naked eye and recorded should correspond to the individual member category. In Step 1, the weighted value of defects and damages on individual members and the visual inspection network chart are considered and evaluated by each type of evaluation method. In Step 2, an evaluation of composite members, which refers to a composite of individual members, such as the dam crest, the upstream slope, downstream slope, approach water path to the spillway, the adjustment unit, winch, water gate, and electrical equipment, etc., are evaluated. In Step 3, individual structures, which refers to composite members such as the dam body, civil facilities of the spillway, and electrical generation equipment, etc., are evaluated. In Step 4, composite members, which refer to a composite of individual structures, such as the dam body, spillway, and other facilities, are evaluated. In Step 5, an evaluation of the entire integrated structure, which is the dam, is conducted. Let's discuss the method of conducting visual inspections according to the type of dam. Dams are largely classified as embankment dams and concrete dams, depending on the construction material. We will first discuss embankment dams, which according to their structures can further be classified into earth-fill dams, homogeneous earth-fill dams, zoned embankment dams, and rock-fill dams. For embankment dams, The type of damages that can occur varies depending on the area. For example, seepages or leakages generally occur in the downstream slope or the banks, and surface damage can be caused by wave actions in the reservoir in the upstream slope. Differential settlement, cracking, erosion, and vegetative growth, etc., can occur on all areas of the dam. There are matters that need to be closely examined in each area during a naked eye inspection of embankment dams. Any cracks that have occurred on the dam crest, and whether there are settlements or sinkholes on the dam crest, and the upstream and downstream slopes must be recorded. The inspector must also be determined whether there are settlements, sliding, or bulges on the upstream and downstream slopes, and whether there is seepage in the downstream slopes and banks. Furthermore, it must also be determined whether any excess vegetation growth or animal burrows are present in the dam body, and whether settlements are occurring on the dam crest or bulges in the slope. Let's take a look at concrete dam inspections. Concrete dams, according to their types, may be categorized further into gravity, arch, roller compacted, and buttress types. Unlike embankment dams that we discussed previously, collapse occurs quickly in concrete dams, which signifies that it is potentially more dangerous. However, erosion by overtopping does not occur in concrete dams, and the collapse of slopes or the risk of piping does not occur either. Concrete dams also have a structure with a steep slope and faces, and difficult vertical access, and thus the safety of inspectors is of utmost importance during site inspections. In the past, rope access inspections were mostly conducted for site inspections, but recently, to resolve the problem of accessibility, devices such as UAV, unmanned aerial vehicle, are being applied. For concrete dams, there is a need to conduct a general inspection on the deterioration of concrete based on cracking, as well as freezing and thawing, alkali aggregate reaction, and so on. Concrete deterioration includes spalling, delamination, disintegration, and other types. Among the many types of defects or damages, structural cracking may be a potential risk factor that must particularly be given further attention. The spillway is a very important facility in terms of safely operating a dam. Since it is easily damaged by high-speed water pressure during a release of flood water, there is a need to perform suitable repairs and supplementations before the release of water after performing a thorough naked eye inspection. The key points to consider during a naked eye inspection include cracks or structural damages to the structure, and damages such as erosion, exfoliation, spalling, abrasion, and others can be caused by cavitation of the concrete slope. Any obstacles, such as impurities that may affect the discharge of flood water in the waterway, and any leakage, efflorescence of other walls, and crazing of the ground slabs are also observed. The intake facility, the outlet, and other additional facilities must generally be inspected in terms of the structural and material defects of the concrete or steel materials, and whether the operational equipment, such as the water gate and valves, are operating properly. The areas underwater that cannot be inspected by the naked eye are normally inspected using divers or an ROV. Looking at the images of the intake facility, cracks, efflorescence, and spalling of concrete are all observed, and the corrosion of steel equipment is also evident. Furthermore, the images of the outlet reveal cracks and delamination of concrete are occurring above the surface. In addition to performing visual inspections to determine the current state within materials that cannot be easily determined solely by visual inspection, such as the strength of concrete and the state of iron corrosion, durability tests must essentially be conducted. Durability tests are conducted on concrete members, and the key test methods include the rebound hardness test for testing the strength of the concrete, and the carbonation test for determining the possibility of iron corrosion. Let's take a closer look at the methods of these tests. A rebound hardness test is conducted to estimate the compression force of the structure from the rebound hardness of the concrete surface. A device called a Schmidt hammer is used. A calculation is made based on the correlation between the rebound reaction displayed by hitting the concrete surface with a Schmidt hammer and the compression strength of the concrete. The rebound hardness value obtained by hitting the surface several times is averaged and calculated according to the set formula. Lastly, the correction value considering the test conditions are added to estimate the compression strength. A carbonation test is a test to examine the possibility of corrosion of rebars inside the concrete. Concrete is naturally alkaline, and when it is exposed to air, it reacts with carbon dioxide and becomes carbonized. And when carbonation occurs deeply within concrete, the possibility of corrosion of rebars increases. The order of the procedure for conducting a carbonation test includes, first, the partial breaking of the concrete surface using a device, such as a drill. And when a phenolphthalein solution is sprayed on the cracked part, the phenolphthalein solution reacts with alkaline materials, changing to a pink hue. Thus, the depth is measured when the phenolphthalein solution has turned pink, and the carbonation depth of the concrete can be determined. By using this method, the possibility of corrosion of the iron may be estimated. Based on naked eye investigations and durability tests, there are difficulties in exploring leaks and cavities on the inside of structures or investigating underwater parts, and there are limitations in managing digital data. This is why geophysical prospecting is needed in order to conduct a closer examination on the safety of facilities. As shown, various geophysical prospecting methods such as electrical resistivity tomography or impact echo are applied. Furthermore, to investigate areas that are difficult to observe with the naked eye, UAV and ROV devices are used. Let's take a closer look at geophysical prospecting. The test method generally applied to determine the leakage of a dam body in an embankment dam is the electrical resistivity tomography method. It is easily applied since water has low electrical resistance. Two electrodes are installed in the dam body to apply the current, and when the potential difference between the electrodes is measured, the resistance can be calculated by a formula, and an electric potential distribution graph may be drawn. When an electric resistivity tomography is conducted on various sides of a dam body using the same method, the results can be combined to ascertain the geological structure or underground water distribution of the banks and within the dam. The second method of testing to determine any leakages in an embankment dam by conducting an electromagnetic test. When electronodes are embedded from the upstream to the downstream of a dam in terms of the length, a voltage is applied to the electronodes. The current flows along the leakage route at low voltage. When currents flow, a magnetic field is formed around the path. Thus, the leakage route of the dam body can be predicted by measuring the intensity of the magnetic field. And when conducted along with the electrical resistivity tomography method, the accuracy of the test may be enhanced. To determine the internal cavity of structures, and the D-bond or delamination between structures and connecting grounds, i.e. exploration or GPR exploration methods can be applied. i.e. exploration sends elastic waves to the ground by hitting the Earth's surface with a hammer to determine the position of cavities and the thickness of structures using the properties of reflection and resonation of boundary surfaces. GPR exploration is a method of interpreting signals reflected by penetrating electromagnetic waves underground to determine the location of iron bars and cavities of the underground stratum structures. The image on the left displays the how, i.e. exploration, and the right displays the how GPR exploration works. Concerning i.e. exploration, in an area believed to be a cavity, signals are reflected, and thus it can be ascertained that shadows occur in different positions in comparison to areas without abnormalities. GPR exploration involves interpreting the portion with bent signals as the portion in which the stratum structure changes. Thus, the determination of a proficient technician is required. Because a dam has a significant scale, inspections by an inspector have restrictions in terms of time and safety, and in terms of access to certain regions, which causes difficulty in visual inspections. The 3D modeling method can resolve these problems by allowing for remote inspections of the facility. The 3D mapping method includes a method of constructing a 3D model of the facility by combining an image captured by a drone and a digital topography model. The 3D scanning method refers to the method of realizing a panorama image of the facility by adding an image captured by a 3D laser scanner device. When these methods are applied to facility inspections, the remote inspection of damages to structures becomes possible, and digital data can be accumulated, which allows for continuous maintenance and management. In the past, underwater research water was conducted by a diver, but the visibility was poor at deeper water levels, which resulted in low accuracy and increased the possibility of missing safety issues. This is why underwater drones are being used to research underwater structures. A drone is controlled by a person on the ground, and the underwater drone is used to obtain ultrasound images based on optical images and sonar to transfer to the ground. Using the underwater drone, the transmitted data can be analyzed and reprocessed to result in a safer and more precise analysis of underwater structures. This video has reprocessed ultrasonic reception data into a 3D model using the 3D sonar device equipped on an underwater drone. Instead of a diver, the underwater drone explores the waters to ascertain the current state of the facilities that could not be seen before. For a safety inspection, the result of a state assessment based on exterior research, a durability test to understand the state of materials, including the rebound hardness method and a carbonation test, and the result of geophysical prospecting, including the state of geological features and the ground or an underwater investigations are combined to ultimately determine the safety level of a facility. The safety levels are classified into the 5 different categories from A to E. A grade level A means the structure is in excellent condition and is in optimum state with no problems. Level B refers to a satisfactory state that requires partial repairs to enhance durability. Level C refers to a normal state that requires simple supplementations on the auxiliary members. Level D refers to an unsatisfactory state that requires urgent repairs and supplementations. And Level E refers to a bad state in which the safety of the facility is at a risk due to severe defects. All facilities are inspected and classified into levels, and in order to increase the safety level compared to the previous inspection results, there must be a clear reason, such as repairs or supplementation.